Jai Hind everyone. I am Shraddha Mishra, Assistant Professor, Department of Information Technology, Ajay Kumar Garg Engineering College. Today we will be learning about posets. So let's proceed. Poset. Partial ordering set. A relation R on a set S is called a partial ordering or partial order if it is reflexive, antisymmetric and transitive. So if there is any set which is reflexive, antisymmetric and transitive, we call it a poset, which is partial ordering set. A set S together with the partial ordering R is called a partially ordered set or poset, and it's denoted by S, R. So here S means the set we're discussing and R is the relation. So set and its relation together make a poset. Example, show that the greater than or equal is a partial ordering on the set of integers. So you have to prove poset means if for this symbol you have to show that it is reflexive, it is antisymmetric and it is transitive. So how do we prove that? First, X is always greater or equal to itself means it is reflexive. It does satisfy this condition, right? Now, here if we talk about the antisymmetric, so x greater than equal to y and y greater than equal to x, then x is equal to y. So, this is antisymmetric. If x is not equal to y, then x is greater than y, but y is not greater than x. Hence, it's antisymmetric. Then transitive, x is greater than equal to y, y greater than equal to z. That very clearly implies that x is greater or equal to z. So, it is transitive. Since it satisfies all the three conditions, we say that it is poset, right? Now, the elements A and B of a poset are called comparable if either A is less than equal to B or B is less than equal to A. The elements A and B for poset are called incomparable if neither A less than equal to B or B less than equal to A. So, if you talk about this poset, so these are the integers 3 and 9 comparable, are 5 and 7 comparable. So, if you see here, 3 and 9, 5, 7, 7, 5, right? So, these are comparable but not these, right? Because z plus means integer and divide by, right? So, 9 can be divided by 3, but 7 can't be divided by 5. Definition 3. If S, less than equal to, it's a poset, and every two elements of set are comparable, S is called a totally ordered or linearly ordered set, and less than equal to, it's called a total ordered or a linear order. Example, if we talk about integer less than equal to. So, if you see here, this is totally ordered because A less than equal to B or B less than equal to A whenever A and B are integers. The poset Z plus this is not totally ordered. Lexicographic order. The words in a dictionary are listed in alphabetic or lexicographic order, which is based on the ordering of the letters in the alphabet. Alright. Now we come to the Hasse diagram. The Hasse diagram of a poset S is a diagram whose vertices represent the element of S and Y is an immediate successor of X in S. Then an edge or line is drawn directed from X to Y. Sometimes, instead of drawing a line directed from X to Y, we take Y at higher level than X and join X and Y by straight line. So, we'll understand with the help of a diagram. Hasse diagram means you have the elements here and you have a relation between them with the help of edges. So, if you see here, draw the Hasse diagram representing the partial ordering A, B. A divides B on these. So, first, let's try to understand the relations between them. We know the elements, we've just randomly drop these elements here. Now we need a relation. So, Hasse diagram means, what is a diagram? You have element, you have vertices and you have edges, right? So, it's an amalgamation of that. That's a Hasse diagram for you. That's a diagram in general, right? So, Hasse diagram, if you say you have the elements, now we have to draw a relation. A divides B. So, does 1 divide 2? Yes, 1 divides all of them, right? So, 1 has a, now 1 divides 2. So, now, if you see here till 12, you can see we have drawn these relations, right? 1 is related to 2, 1 is related to 3, 2 is related to 4 and so on. So, you can see here that 2 and 3 are divided by 1, 4 is divided by 2, 6 is divided by 3, 8 is divided by 4, and 12 is divided by 6, and 12 is also divided by 3, and 12 is also divided by 1. So you can say there's a relation. Then 4 is divided by 12, so there's a relation. 2 is divided by 6, so there's a relation, right? And 2, so you can see these are the relations. So this is a Hasse diagram, means you have the elements and you have the relation between them. Similarly, here you can see, draw the Hasse diagram of the partial ordering A comma B. A less is a subset of B on the power set PS, where S is equal to A, B, C. So you can see here, A, B, C were our elements and we had to draw the power set. So what are the power set? A, firstly phi is a power set of all elements, right? A, then B and C. So first phi and the elements itself, then we'll group. For 3, what it will be? A comma B and A comma C, right? So we are sorted with A. Now B, C comma A and C comma B, and in the third it's going to be all the elements together, which is A comma B comma C. So you see all of these elements are listed here. 0, which is phi, A, B, C, A, C, right? Now, so these are so many power set, but out of so many power set, we have to draw the relation where A is a subset of B. So according to that, phi is a subset of all sets. We had this here at the very bottom. A, B, C will definitely be a subset of phi, because phi is a subset of all the sets. A comma C, so A is already included, so it is a subset. A comma B is also a subset because it's part here. A, B, C will definitely be a subset of it. Similarly, you see here B comma C will be a subset of B. And similarly, if you see here, for this A comma B comma C will also be a subset for B. So similarly, we have these relations drawn. Maximal and minimal elements. So what do you understand by maximal? The one which is at the peak, and minimal which is at the bottom. So maximum and minimal, as the term says, for example, if you see here, 8 and 12 are the top, so there's a maximal, 1 is at the bottom, so it's a minimal. Now, how do we understand it? With the help of a maths. An element A belongs to S is a maximal. In the poset S, there is no B which belongs to S, such that AB. Similarly, an element A which belongs to S is minimal if there is no B which belongs to S, such that there's an element A which belongs to S is greatest element for the poset. So you can see here that there are certain criteria. That means, in simple words, if I understand all of this, maximal means that element is going to be greater than all the other elements, satisfying condition, and minimal means that element is going to be lesser in comparison in all conditions compared to all the other elements. Now, if we understand this, here the upper bound is 6 and 12 for A and the lower bound is 1 and 2. So you can clearly say that we can't simply say the upper bound and lower bound by looking, okay, these are in the tops, they'll be upper bound, this is the bottom, lower. No, because you can see the answer is clearly 6 and 1, right? So how do you define this? We define it like this, because let A be a subset of a poset S less than equal to, if U is an element of A such that A less than equal to U, for all elements A belongs to A, then U is called an upper bound of A. So if you see here, this A set is given to us 2 and 6. So in these 2 and 6, if we talk, the upper bound of A is going to be 6 and 12, means all what elements among 2 and 6. So 6 is greater and 6 se upar is 12. Lower bound in this is 1 and that element itself, right? So it is a very respective and a very comparative analysis you have to do. Only the objects which they are asking us to consider right now here in this example is 2 and 6. So we have only considered these two elements, 2 and 6. So for 6, if you talk about these two levels, okay, in this parameter, which is at a higher level, the number itself will definitely be in 2 and 6, 6 is definitely higher. Or 6 se bhi upar kya hai? There is 12, right, in its vicinity. In 2 and 6, which is the smaller one? 2. So that number itself, and 2 se kam kya hai? 1 here, which is directly related. So upper bound and lower bound. Alright, we have one more example. I think with the help of example, it's going to be better understood than just reading the theory. So you have another diagram for you. You see here, A1 is your D and E, as you can see denoted by blue, and A2 is your B and C here. So least upper bound of A1 is F. Now, A1 means DE. So DE ka least upper bound is F. So what do you understand by least upper bound? Upper bound, right? So in this least upper bound, which is your F, it comes down to this, the immediate next, right? Least upper bound means upper bound to dono hai, D or E ke bound. If you say upper which bounds them is both F and G, but in that least is which one? It is F, the very one which is the very next. So A1 has no greatest lower bound, right? If I talk about its greatest lower bound, it doesn't have, right? Greatest means it is 1. If there are 2 people, then it is not greatest, definitely, right? So for D and E, this ye bhi ladai karega, ye bhi ladai karega. I'll be the greatest, he'll be like I'll be greatest. So they'll be in conflict with each other. So we keep it safe, neutral. Okay, dono hi nahi hai. So there is no greatest lower bound for it. But here very clearly there's a very clear winner. Now A2 is B comma C. So A2 has no least upper bound. Now if you talk about these two, there is for this for B you have D as his master, and for C you have E as his master. Now though these two master will fight, I am the greatest master, he'll say I am the greatest master, they both will say, but we both are at the same level. So where do we come to a conclusion? So we say, okay, there is no greatest lower bound for it, no greatest upper bound for it. Now here A2 has no least upper bound. Greatest lower bound of A2 is A. But yes, very clearly, it has a greatest lower bound, which is A, right? Because lower bound means this is at a higher level. Because lower bound to dono hai, A and Z. But inme se kaun sa hai lower bound? Greatest one, which is A. So answer here is F and A respectively for LUB and for GLB. Lattices. A partially ordered set in which every pair of elements has both a least upper bound and a greatest lower bound is called a lattice. Example, determine whether the following posets are lattices. So if you see here, you can see, so what is a lattice? Lattice is very clearly they are saying, pehle to lattice, it has to be a poset, it has to be partially ordering set, is going to be a set and it is going to have a relation, so it is going to be a poset. What is the second condition? It needs to have a LUB and it needs to have a GLB. Greatest lower bound and upper bound it has to have. So since we can draw it in Hasse diagram, they are definitely posets. It's given also that these are posets. You just have to check for lattice. And lattice means it needs to have a least upper bound and the greatest lower bound. GLB and LUB needs to have. So we have to check for that. Just seeing by the face of it, we can maybe do a wild guess with that if you have a peak at the top in the end, means it has a greatest, it does have an upper bound and a lower bound very clearly, because if it has a tip. But just by seeing the face of it, we cannot come to the verdict. We have to also recheck with the process. So if you see here, very clearly for these two elements, there is these two which are the upper bound. In these, the least is E. So it clearly has a LUB, which is E, which wins here. For C and D, it clearly has two lower bounds in that the greatest lower bound is B. So E and F, since it has a very clear LUB and GLB, it is a lattice. Right? Lattice means it has to have a very clear GLB and LUB, which is least upper bound and greatest lower bound. Now, what about this? So you see here, if we talk about D and C here, they definitely have one least upper bound. But do they have any lower bound? No, because they both will fight. And if any lattice, we have also read in chemistry, right? Any bond is stable if all are at equilibrium, right? And if you see here, if these B and C will be in conflict, so will this be stable? No. So lattice means every element has to be stable. So if you see this diagram, you can see that B, though it has a least upper bound, there is no greatest lower bound because there is no clear winner. D will say, he is my student, he has to win. E will say, he is my student, he has to win. Now they will fight, so this lattice will be unstable, hence it's not even a lattice. They will say, okay, disqualified. Okay, because there's a lot of fighting within your group. How do we declare a clear winner? Now, so if you see here, B and C, they have definitely a least upper, they definitely have a greatest lower bound, but they don't have least upper bound. Similarly, they will say, my teacher will win, my teacher will win. They'll say, you're again fighting, so they're disqualified. So it's not even a lattice. Why? Because there are a lot of conflicts here. There's conflict for least upper bound and greatest lower bound. So there's no clear winner. If there's no clear winner, the lattice is not stable, hence it's not a lattice. See here. You have to pick any two elements and check for them. So if you see here E and G, they definitely have a least upper bound here. And they definitely have a greatest lower bound here. Right? So since we have a very clear least upper bound and the greatest lower bound, it is a lattice most certainly. Yay. Right? So it is a lattice. So, yay. Next, is this Posets Z plus divide a lattice? Now, when you are given these kind of questions, right, you have to, you can use a basic common sense also and solve it. And if it comes for more marks, you have to take an example of certain elements and prove it with the help of a diagram. But since I assume this is for 2 marks, we can directly say that GCD-AB is the greatest lower bound and the LCM, right? So here for Z plus means integer divide by. So for integer divide by, is it a lattice? So it is very clear what is HCF, highest common factor. What is LCM? Least common factor. So if you see least common multiple, so you know that it definitely has an HCF and LCM, hence it's a lattice very clearly. So we can prove it with the theory only. Determine whether the Posets 1, 2, 3, 4, 5, divide by and this are lattices. So we will try to prove. In this, you can say 2 and 3 has no LUB. Why? Because 2 will certainly not divide 3, right? And here if you see that every element, right, will divide itself. 16 will divide 8, 16 will divide 4, 16 will divide 2. Similarly, you can see. So since each element will be related to each other, so here they will very clearly have a least upper bound and the greatest lower bound. So yes, it is a lattice. But here won't be lattice. Why? Because we won't be able to draw any conclusion. Because does these random number divide itself? No. 2 will definitely divide 4, but will 2 divide 3? No. But here if you see, every element will divide each other. So here in these elements you can see. So this is Hasse diagram and lattice field. So lattice is a very, very important topic for your AQ2 and for your university exam. So here you should understand. So let's summarize it. So what do you understand by Poset? Poset is S, any set having a relation R. So Poset is denoted by S, R. Hasse diagram, with the help of vertices and edges, if you are able to draw relation, then it is a Hasse diagram. And lattice clearly means if you have a least upper bound and a greatest lower bound, then it is a lattice. It has to be certainly a Poset. Okay. So thank you so much everyone. Have a wonderful day. Hope you enjoy.